Today I'm going to say a little bit about what we did to fill a gap in a module which we had with a bit of game theory, which is something that was new to us at the Open University. And so I'm just going to say a little bit about how we went about it and indeed some of the constraints that came into the process. Um, a little bit of background first. So we had a 30 credit module, third year 30 credit module, which you could broadly describe as discrete maths. I'm not going to go into great detail. And it had been running essentially unchanged for over 20 years. I think it had first run in 1996. And the nature of OU teaching is, of course, these things come in books. So the ability to change these things is somewhat limited from year to year. Surprisingly, when it came to reproducing this thing about 4 years ago, really most of the material was still reasonably relevant. You could update it a bit and so on and so forth. But there were chunks of it which were just too long in the tooth and just not relevant anymore. There's stuff about sort of drawing pictures of giraffes with sort of pixelated black and white pixels and things. And the world has moved on somewhat since then, for example. So we had about 7.5 credit gap in this module, which we needed to put something into. And we had a little look around about what we might be able to do. You know, we could do more of the discrete maths we're currently doing or whatever. And somehow the idea of game theory came along. Partly because this module, although we regard it as something in pure maths, is taken by a whole bunch of other students from different degree pathways. Engineers and economists are probably the most common ones, at least historically, but now increasingly data science is coming in. Now the data scientists probably have a reasonable mathematical background, but some of the engineers have done literally maybe 30 credits worth of mathematics study at first year level, and that's it. So while we wanted to write a module that is in pure mathematics and is rigorous, we also needed to make sure that it was going to be accessible to those who really hadn't seen much mathematics previously. So that was kind of the constraints. And the question was, you know, can we get game theory in there? What do we need to meaningfully put some game theory in? And you know, can we do it? Okay, so here's what the new module essentially looks something like this. So it's divided into 4 books. I won't talk about the other 3, of course, but book A is sort of standard graph theory. Book B is sort of networky type stuff, which is, you can largely think of sort of algorithms, that sort of thing. Book C is the bit we're going to talk about today, which is sort of game theory. And then the last one's about designs. Now, the study of how these things are studied, books A and B were kind of interleaved with each other, and books C and D were interleaved. So you didn't study it all in one big fell swoop, that were. You sort of study a bit, and then you switch to another book and switch back and so on. Okay, so this is the structure of the module, and I've described it as sort of playful blend of applications of algorithmic methods. There's plenty of those in network type stuff, together with some of the rigorous mathematical proofs, the sorts of things you find in sort of graph theory type courses and so on. So that's kind of how the rest of it all sticks together, and that's where the game theory sits. So the students will have studied some graph theory, and that's about it. Okay, so we sort of roughly made up a little list of things that we probably needed to avoid. So things that we really didn't want to touch with anything were things like calculus. That's not so difficult to achieve because, I mean, calculus does come into game theory, but only at much later stages. So if you stick with static games or something, we should be able to get away without needing to worry too much about calculus. Linear algebra is a little bit more problematic. We can sort of expect students to be able to multiply matrices, but that's about it. Analysis, also perhaps a little bit problematic. Certainly things like functional analysis, which kind of sits behind things like Brouwer's fixed point theorem, which somehow underpins Nash's equilibrium theorem, which is one of the big sort of central things you might expect to see in game theory. So that's a sort of gap which we needed to worry about. And then probably the other thing which we needed to assume zero knowledge of was probability, which is, of course, in game theory is kind of problematic because we're talking about mixed strategies where you might want to sort of, you know, choose some probability between 0 and 1 and so on. So we probably needed to fill that gap in order to say anything really meaningful about game theory. On the other hand, we do have various things available to us. Of course, the students have just been studying all sorts of graph theory and indeed trees, and indeed various game tree type things were drawn just by way of examples in some of the earlier graph theory units from the previous module. So we could keep that, and that would help us then to link into the game theory that we were doing. And as I say, things like basic matrix manipulation, multiplying matrices, vectors, that sort of thing, is to do. So, and at the bottom, I should say, if you're bored, you can just have a little look at these are just a random selection of images from our module, trying to give a sense of the sort of playful nature, if you like, of our module. Okay, so we've got these constraints, and then there were various things that we wanted to include and probably things that we should include. So in particular, I wanted to include something about combinatorial games. I like combinatorial game theory. It's quite fun, and there's some nice stuff in there. And it doesn't really require many prerequisites. So this seemed like a reasonable thing to do. But of course, for a lot of people, that's not really game theory. To an economist, that's, it's a completely different thing to actual game theory. And we also wanted to include something about applications because that's the nature of the module as a whole, is that a lot of the stuff is application focused, even though there's a sort of rigor at the bottom of it. Things that we really should include, and this is something to do with some of it are just things like you have to talk about the prisoner's dilemma if you're going to do game theory, and Nash equilibria, that sort of thing, something about zero-sum games. These things all have to come in here. And then usually most textbooks that you look at will say something about rational play and strategy and that sort of thing. And we wanted to try and take a sort of reasonably rigorous approach to that. And then, of course, the other thing which I said is that we were sort of assuming essentially zero probability. So we needed to do something about that before we could really say too much along those lines. But actually, you can get away with introducing probability in a very sort of basic sense, which is perfectly, compatible with any other probability that you might have studied previously. But you can also just teach them the little bits that they need to know and run with that. Okay, so we looked at various textbooks along the way. I mean, obviously, the way the OU works is we write our own books. And in fact, here is the resulting book that it's not going to be blurry, isn't it? Well, you can see it's a blurry book. That's the result of what we did. But obviously, there were various places where we wanted to draw on some ideas, get some various things. And of course, if you're in another university, you might just want to use a textbook. And there were 4 which we found particularly helpful for sort of ideas. The first one is the one on the left, DeVos and Kent, Game Theory, a Playful Introduction. That we found generally a really lovely, gentle introduction. It actually begins with combinatorial game theory, which kind of gave me some confidence that maybe this is the right way to go. But it also then covers zero-sum games and it covers everything. So we took quite a lot of sort of inspiration from that particular book. This second one by Straffin, Game Theory and Strategy, is a rather older book, and we didn't use that much from it, but it did have some nice discussions about von Neumann lotteries and so on, which was sort of quite a useful sort of place to get some ideas. This third one by von Stengel on Game Theory Basics is quite a recent book. It came out, I think, just at the beginning of when we were actually writing these units on game theory. And it takes quite a rigorous approach. So in some sense, that was quite useful for the slightly more rigorous ways that one might look at sort of Nash equilibria and so on. And then finally, this one, which is a lovely textbook on combinatorial game theory, and is just a lovely text. So I thought I'd include that there. Okay, so these are the kind of 4 textbooks that we drew on. I should say that neither I, as one of the authors, nor the other author had really done much game theory before we came to trying to teach game theory to a bunch of students. So we were very much relying on textbooks at the beginning to get some kind of sense of what we might be able to do. Okay, so here's what came out. The structure of the module as a whole meant that we were going to have 3 chapters inside this book C. And this was roughly the way it was going to be done. So chapter 1 was somehow introductory material. I'll go into the detail in a moment. Chapter 2 was going to be some stuff on zero-sum games. And then chapter 3 was going to look at Nash equilibria and see what we could say there. Okay, so here's a little bit more detail in chapter 1, which is kind of chopped into two halves. The first half was kind of generic introduction to game theory. What is a game? You know, some kind of formalization of that notion. Section 2 was a little bit curious because we sort of dived straight into the notion of a utility function that, you know, each person might value a particular outcome more than another a particular outcome or whatever. And the notion of the von Neumann's lotteries for finding utility functions becomes quite a sort of rigorous way to get somebody to understand how utility might work and how it might vary for different people. And yet the von Neumann's lottery is a relatively straightforward process that you can operate in order to try and sort of compute utility functions. And then we went on to combinatorial game theory in the second half. So some generic combinatorial games with drawing game trees, this sort of thing. Lots of lovely space for sort of really rigorous proofs in here, though, which, you know, you can talk about winning strategies for particular games or whatever. And then in section 4, the specific case of impartial games as a subclass of combinatorial games, which of course has this celebrated Sprague-Grundy theorem, which tells you that basically every impartial game is equivalent to this stone picking up game nim, and there's various things that you can compute around that as well. And so here's a game tree at the bottom, for example, of a game called Chomp, and the things on the side are the equivalent nim games, which you can compute. So that's chapter 1. Chapter 2 is what you might expect from zero-sum games, really. Here we really have to start talking about the notions of strategy. So we have pure strategies, we have mixed strategies, which of course requires some of this is where the probability comes in. So we didn't have to do it straight away. We could sort of leave it till this point. And then and then carrying on to sort of finding actual solutions to zero-sum games, the so-called von Neumann solutions, including various cases. So obviously for 2x2 games, it's reasonably straightforward. You just have 2x2 matrix and so on. And in some sort of slightly more complicated games where, say, one of your players has n choices or the other one has m choices, then there are ways you can find solutions. To go further than that would start to get a bit tricky at this level, but it gives people a really good sense of how a good sense of how zero-sum games operate, and the idea is to whet their appetite to be able to go and take more, look at more if they wanted to. And then finally we close with some applications, sort of problem solving, setting up things as games, that sort of business, and indeed a section on voting systems, which is where this final picture comes from. I was impressed by my colleague's ability to draw a sort of natural looking ticks drawn coffee splodge over a table, which is a margin table from an election, with the idea that students then have to be able to reconstruct the numbers. Okay. And then finally, the third chapter is on general games and Nash equilibria. So again, we start with the introductory material, how it connects to zero-sum games, that sort of business, and then we go into essentially a discussion about the prisoner's dilemma. And of course, the key issue about the prisoner's dilemma is, if you know what it is that while if you look at each individual, you've got these two people in prison, and they're both given this choice to either cooperate with their captors or to refuse to cooperate. And if they cooperate, then they might get a lighter sentence because they've dobbed their partner in crime in it, as it were. But of course, if they both decide to cooperate, then they both end up getting dobbed in it, and so they end up with a worse outcome. So if you study the game theory, it says that if you follow your individual preferences, then you end up actually, both of you end up saying, oh, I'm going to cooperate with my captors, at which point you both end up with a worse outcome than if you'd worked for the sort of social good, as it were. And that's a sort of conflict between social solutions, if you like, and solutions for individuals, which is sort of captured in this notion of Pareto optimality. So we discuss a bit there, and we end up getting people to draw Pareto fronts in payoff polygons, like the picture at the bottom, that sort of thing. And indeed, that gave us an opportunity to recycle some of the material that we were going to be losing on sort of convex hulls of shapes and things from the previous module. And it was like, oh, well, actually, we need to be able to teach some of this stuff again, so we could import that. So that was a win from our internal point of view. And then, of course, in general games, your solutions look like something like Nash equilibria. So we need to say something about that. And so two sections essentially on that. The first one is about Nash equilibria in general. Obviously, pure ones and mixed ones in the same way as pure strategies and mixed strategies in the zero-sum games. And then the notion of being able to verify that a particular pair of strategies forms the Nash equilibrium because one has a best response to the other and so on. And you can do all this quite rigorously. We could then state Nash's equilibrium theorem, which just tells you that there is always some Nash equilibrium in any game. But the proof of that is rather more involved. And as I mentioned earlier, it requires Brouwer's fixed point theorem and various other things. So to go into the proof of that would have required rather more maths than we could assume in our students, and would have taken up quite a lot of space, given we only had 7.5 credits as well. And then, so having done sort of Nash equilibria in general, we then go into the case of 2x2 games, where you can prove the theorem in a much more easy way, just by sort of considering what happens in that specific case, because you don't have these sort of convex polytopes of sort of higher dimensions. And so there's that whole process. And indeed, in the midst of this as well, I should say something slightly unusual, which we added in here, for those who know about game theories, is you get these Nash equilibria, and quite often you get more than one solution to a particular game. And then you go, well, okay, I've got two solutions. So what should the person do? And is there some way of choosing between the two equilibria? And there's a sort of slightly non-scientific approach there, but that then introduces the idea that you can have a sort of discussion about, whether this is scientifically rigorous or not. Okay, and then at the end, various applications. There's a thing called the Cournot duopoly, which is all very sort of standard, if you like, in sort of game theory settings. We did have to dabble a little bit in very, very basic calculus there to get to the end, but it was really nothing more than differentiating some function. And then also slightly more fun, and this we didn't really assess this, but a discussion about evolutionary biology and this cleaner fish which goes around eating the mucus off a host, and of course the cleaner fish might be tempted to cheat and nibble some of the nice protective coating that this fish has on it, as well as just the sort of microbes that are living on it. And of course, the fish which is being cleaned, the client, has the opportunity, of course, of eating the cleaner fish as well. So you end up with this sort of evolutionary circumstance where the cleaner fish and the clients end up living in some kind of symbiosis, which has been modeled in game theory. Okay, I should say a little bit about assessment. So how did we assess this? Well, the game theory part appeared in 3 tutor-marked assignments, i.e. written assignments, and the questions were a typical mixture of use the method to do whatever, so that sort of turn the handle type questions, and also prove that such and such is whatever. So we do tend to have a bit of a mixture like that. Of course, the use the method to ones are sort of easier, and that tends to give people a reasonable number of marks. But then, of course, you can use the more rigorous questions to sort of distinguish between the stronger students. Then we also have, at the end of the module, we have a computer marked assignment, of which 6 of the questions, so a quarter of the questions, would be on game theory. And these are in a sort of revision type assignment, and it's to help students revise as they're preparing. And all of these questions, I should say, were written using Stack. An example of a question, this is not a question from that particular assignment, because that would be a spoiler, but this is from a practice quiz which are sort of available through the year. But this is the sort of thing you can do. So you can create, in this case, a game on a combinatorial game theory question about determining the types of a particular combinatorial game. And you can code all this stuff up in Stack. And then, of course, besides this, of course, the most of the assessment is done in a remote exam, as is the way with quite a lot of the modules at the Open University. And in that case, there will be, on the game theory part, there'll be 3 shortish questions and then 1 longer question. So again, the short questions would be sort of usually fairly routine things where we expect most people to get the marks, and then the longer question can get progressively harder and more sort of demanding as you get towards the end of it. As I say, similar composition to the tutor marked assignments. Okay, and then last thing I should say is a little bit of feedback. So we ran this course was taught for the first time in 2023 to 24. So we're just now in the middle of our sort of second running. In fact, the students have just started studying a game theory section about a week ago. And we got various bits of feedback, of course. So various people, the first person was really enjoyed book C and thought the explanations were clear. Overall, they enjoyed the module very much and they liked it, very good. And then once the basic ideas sank in, the game's topics became reasonably straightforward to grasp, and there's a flow from C1 to C2 to C3. So those are the 3 game theory chapters. So that student, at least, that was, I think, in response to were there any parts which you found particularly easy. So they didn't find this particularly demanding, but then, of course, that one has to determine whether that student was a math student who's done lots of maths already, or whether it's a sort of engineering or economist who might have slightly less mathematical background. So responses would vary depending on what that person was. And then one person who was very happy, this best module they've studied since leaving school. And remember, Open University students tend to be, they can be of any age whatsoever. So that doesn't necessarily mean the person left school 2 years ago. And then finally, just for a bit of balance, the game theory section was mainly clear. Well, that's damnation by faint praise, I suppose. But I think the coverage of Pareto optimality could be a bit better explained. Okay, well, that's some feedback which we can take into account. That's everything I want to say. Thanks very much for your attention. And I guess somebody wants to share some questions.
Indeed, yes. Thanks very much for that. People can actually react and give applause and things. There's a little under the react button. I think people can see that. Some people have managed to find it. So yes. So do we have any questions? Because we don't seem to have any questions in the open questions. If some, the first question is, how well did the students do on the assessment?
I think they did okay. From memory, so the way our assessment we get sort of high level data. So I mean, I'd say on the exam, which I marked, it was pleasing to see that they largely managed to do what you wanted them to be able to do. You know, they constructed trees. They did well in the bits we hoped they would do well in, and like constructing game trees and so on. And then as the sort of long question wore on, people began to sort of drop out and sort of give up at appropriate stages. And I think we essentially got the mark distribution that we wanted, as it were. So, you know, gratifyingly, I think most students seem to be able to do it. And there wasn't any noticeable difference between the assignments which had game theory on them and the assignments of, say, the first half of the module, which, of course, is much more well understood. We knew much more about it because it had been running for 25 years previously. So I'd say, I mean, yeah, I think they did as we expected them to do, and we got a nice distribution.
Right. Okay. Thanks for that. We don't seem to have any more questions, but if people do have any more questions, they can stick it into the Q&A, and maybe Robert can answer them later. And you can see the answer when we put it up on the website. Okay. So thanks again, Robert, for the talk there.